Good afternoon. Thank you very much for joining us tonight at this Creative Romandie Meetup. So very happy to see you. I will just share my screen and to, as always, introduce a little bit what we are doing, why we are doing this, and who are the speakers joining us tonight. So where we are the four speakers, myself and the three speakers presenters today in a Google Meet room, and then we stream live on YouTube where you are attending, and it would be great if you have any question to participate in the chat, ask in the chat, and like there is a 30-second delay, I would be happy to either my colleague Raphael will answer directly on the chat, or I will be interrupting or waiting at the end of the presentation and ask directly the speakers. So to start and to know a little bit where you all guys from, to know and like this, so we can wait a couple more minutes if there are some people joining a little bit late. I invite you to join with Slido, so it makes it a little bit more interactive, and we'll have three questions to know today. So first of all, to know a little bit, where are you joining us from? So please take out your cell phone and scan the QR code and please let us know. So I see a couple of people joining. Vevey, Écublanc, Echelon we have as well. I see on YouTube that we are at least 15 people. So please don't hesitate to connect. Up, I will share the up where to see a little bit what we have, where people are connecting us, joining us from. And so as soon as more people are joining and letting us know where they are coming from, we will get back to the topic and to know a little bit about tonight's experience and so we are joined by Thomas Graf from Isovalent to introduce Cilium, networking security and observability provider. Then we will be with Adrian from Vision, so managing Kubernetes clusters as cattle with Project Sync. We will have a 5-minute break, and then afterward, we will be joined by Philipp Strube, the founder and CEO of Kubestack, which is a framework for teams building a Kubernetes platform using Terraform with a developer experience focus. So today, without waiting, I will introduce to you Thomas. So Thomas, if you want, I'll leave you the stage and please introduce us to Cilium.
Awesome. Thanks a lot, Terry. I'm Thomas. Nice to meet all of you. Let me share my screen so you can see my slides as well. Let me know once you can see the slide.
All good?
Excellent. So my name is Thomas Graf. I'm CTO and co-founder of Isovalent and one of the co-creators of Cilium. I'm also one of the co-inventors of eBPF. I'm going to talk about Cilium, a open source project that provides cloud native networking, security, and observability. But before we dive into that, to kind of resolve potential confusion, Isovalent, Cilium, what is what? So Isovalent, that's the company behind Cilium. We're a VC-funded company with roots in Switzerland and in the US, so we're dual headquarters in the US in Mountain View and in Switzerland, pretty much like kind of split between the French-speaking and German-speaking part of Switzerland, but actually spread across the world. We have a remote culture, so we have people across Europe and across the US. We're really a company that focuses on open source, so we have a lot of knowledge in Linux. My personal background is Linux kernel development. I was at Red Hat for 10 years, for almost 10 years, 9.5 years, working on the Linux kernel, mostly networking and security, but we also have distributed systems people and so on. We really focus on networking, eBPF, and Cilium. So today we are talking primarily about Cilium and eBPF, which are the open source projects. The company Isovalent is the main contributor to Cilium at this point, no longer the only company, of course, but we also provide an enterprise distribution. So if you are interested in leveraging Cilium in a production environment, in a critical environment, feel free to reach out to us and we can give you an enterprise-grade Cilium distribution. But let's dive into Cilium because I think that's what you're all here for. So we'll first start with a nutshell and then actually dive a bit into eBPF, which is the foundational technology behind it. So Cilium provides networking and load balancing. Most know us for its CNI, container networking infrastructure or interface capability, which is the networking layer of Kubernetes. But we can also do load balancing Kubernetes services, north-south load balancing into clusters. We can do multi-cluster. We can even act as a VM gateway to interact or to embed virtual machines or metal machines into Kubernetes clusters. Well, we can do a lot more. Obviously, we implement network policy, but then we go further and provide extended network security, for example, with transparent encryption and with identity-based enforcement. We'll go into details here. But these days, networking and security is no longer sufficient. What's becoming more and more crucial is actually providing observability, metrics, flow logs, service dependency graphs, and so on. We'll learn more as we dive deeper. What's really crucial, what's really key about Cilium is that everything that is Cilium is based on eBPF. I'm not sure how many of you have heard of eBPF, but it's a revolutionary technology in the Linux kernel, and we'll learn a bit more about that next because I think that's really crucial to actually understand. eBPF, Extended Birthplate Packet Filter. What is eBPF? eBPF is actually relatively simple to understand. It's the ability to execute code when a certain event in the Linux kernel is being invoked. I'm using a very simple example here. Every time a system call is being invoked. For example, when a process is executing the exec system call, for example, if you're running a bash shell and you're executing a command, the bash shell will fork and then execute or run an exec system call to run a command, a new binary. So when that system call happens, you can run a eBPF program very similar to how you can run a JavaScript program as part of your web browser and execute some logic when that event happens. So this could look something like this. This is pseudo C code which would execute and let me turn off Slack here. I'm not sure whether you can see that. There we go. And execute some code time the exec system call is being invoked. In this case, it's actually just exposing some visibility and to, for example, send an event to user space every time a system call is being invoked. This is like an actual practical example on how you can do system call tracing, because you can send a small little message every time a system call is being invoked, and you can do that for every system call that is being done. eBPF can do the same logic in a variety of different hook points, from system calls, trace points, network packets, storage interactions, even user space functions, and so on. This is essentially allowing the Linux kernel to become programmable. Why is this such a big deal? Let's learn about this. So as I mentioned, in my former life before founding Isovalent and creating Cilium, I was a kernel developer. So my life was about writing Linux kernel features. And as you know, the cycle of Linux kernel development is pretty long. So in the event of, let's say, an application developer is in need of a new feature and the Linux kernel did not offer this feature yet, for example, hey, I want to observe my new app here, the application developer would have to come up to the kernel developer and say, hey, kernel developer, please add this feature to the Linux kernel so I can observe my app. The kernel developer would then have to find consensus in the entire kernel community to get this change in. This by itself was very complicated because obviously every single change to the Linux kernel like bears some cost, and this cost has to be paid by the entire Linux kernel user base, from like supercomputer users to Android mobile phones, right? So this was challenging, but then it got even worse. That once you got your change in, it took years for enterprise distributions to actually adopt kernel versions with that change. So for sometimes this would take even up to 5 years. So from the point of an application developer requiring a new feature to observe an app to the point of being able to use that feature, it could take up to 5 years. This essentially rendered the Linux kernel as an absolutely suboptimal place to do any sort of innovation. And this is why we have seen a lot of user space networking. We've seen a lot of user space driven applications that for example, observing applications and so on. We've also seen like Linux kernel modules being misused to, for example, provide visibility, even though Linux kernel modules have been meant to be used for drivers and not really for like potentially insecure code. So this was not ideal, and it meant that from a Linux kernel development perspective, there's not that much we could do to actually innovate because we could not get it into the hands of users directly. eBPF is changing this forever, and this is why this is such a fundamental technology. It means that because we can reprogram the kernel, very similar to how JavaScript is doing this for the browser, we can change the behavior and add additional functionality and load that at runtime. So if we take the same example, the application developer can come up and say, hey, I need this new feature. Then instead of a kernel developer, an eBPF developer can respond and say, sure, let me just quickly write this eBPF program that will add the functionality that you need. And a couple of days later can come back and say, hey, you can now load your Linux kernel program, or your eBPF program, and add the functionality to your kernel. And it gets even better. You don't have to reboot your machine at all. You can simply run it, and you can unload it. You can load new versions, and so on. So this has significantly changed, or is significantly changing the impact of kernel developer or kernel development features. If you look at the overall landscape, like what has this eBPF technology actually unlocked? We see 3 different layers. We see the main 3 use cases, and most eBPF use cases fall into these 3 topics: networking, security, and observability and tracing. Then we have a set of projects which actually implement these use cases or provide them. We see something like BCC, Cilium, Falcon, Katran, BPF Trace. There are numerous more. I've just listed the ones on eBPF.io, kind of the bigger projects. Then we have a list of SDKs, and this is kind of the like bridging us into the kernel runtime there. The SDKs enable use of Cilium, or use of eBPF, which is a very low-level technology, by using higher level languages such as Golang, C++, Rust, Python, and so on. And then on the bottom layer, this is where the kernel runtime sits. So this is kind of like the JavaScript engine. This is what's executing eBPF programs, and you will see a couple of boxes in here. And understanding these boxes is actually very crucial because this is the difference to Linux kernel modules. Because some of you may now say, well, if I was able to run or load Linux kernel modules before, why do I even need eBPF programs? I was able to load the modules anyway. Like I could just have implemented my new functionality as a Linux kernel module. The main difference to an eBPF program is that it passes through verifier and a just-in-time compiler. The verifier will ensure that eBPF programs are safe to run and will refuse to run them and run them in a sandbox, very similar to a JavaScript program. The just-in-time compiler, again, same as for JavaScript and other languages, will take generic bytecode, which is independent of the CPU you are running, and just-in-time compile that into your CPU instruction set that you're running on your machine, which means the code will, in the end, run as efficiently as if you would recompile your kernel. Then we have maps. Maps allow to share data between programs and to user space. So that's how we can expose statistics, notifications, events, configure our programs, and so on. And we also have a set of kernel helper API calls. Unlike kernel modules will call directly into kernel functions. So you will have to port your kernel modules to every single kernel version that is out there. As soon as a function no longer exists or a new function is renamed or something, you will have to change kernel module source code. With eBPF programs, they're leveraging a stable set of API calls which never change. They only get extended, which means programs are portable across kernel versions. And that's the big difference. And that's kind of the revolution that is happening right now. All of a sudden, we can evolve and change the kernel at runtime and innovate. So we're seeing something very similar to what we have seen in the browser landscape 20 years ago when we went from like Netscape Navigator and having to install new versions of our web browsers to view certain websites, to JavaScript powering entire word processing software applications, completely replacing Microsoft Word, for example, which I think most people would have never seen possible when they would have looked at a web browser 20 years ago. All of this has led to the creation of an eBPF Foundation with the founding members that you can see here. The eBPF Foundation is, with the exception of Microsoft, it consists of kind of the companies that have been funding most of the development. I would say most of it is actually Facebook and Isovalent. Netflix has been very prominent with BCC and BPF Trace. Maybe some of you have seen talks from Brendan Gregg. That's mostly one level above the kernel runtime. Microsoft was also included because they've actually ported eBPF to Windows kernel as well. So it's now possible to run eBPF programs on Windows. It's no longer Linux-specific technology. So switching gears a bit, like this is eBPF. Like, what is Cilium making out of this eBPF technology? Why do we need this? Why does it make a difference? It's great that we can now innovate in the kernel space again and get new innovations into the hands of users. Why does that matter? So let's look a bit and look at the fundamental difference to what Cilium does differently because of eBPF. Traditionally in networking, we had a very device-centric view on how networking was done. We went from a phase of hardware networking where we literally plugged in physical cables to software-defined networking throughout the virtualization age. Some of you may be using VMware NSX, for example, or Open vSwitch or another virtualization technology. This age was still, it was now software, or it is now software, but it's still using very networking specific terminology. We're talking virtual routers, virtual switches, virtual cables, essentially, virtual Ethernet cables. It's the same terminology, same way of doing things, just in software. We haven't actually fully leveraged the power of software by being able to do everything. We have just ported concepts from the hardware networking world over to software. What we are doing is actually expanding that further into a service-centric networking world, which means we are ignoring, to the most extent, for example, IP addresses, because nobody cares what IP address a container has, for example. What users care about is running services. So when we, for example, do service discovery, we can do this based on names regardless of what IP addresses are given out. For example, we can even have overlapping IP addresses across clusters and still do service discovery. When we do network policy or segmentation, we care about service names and labels and metadata and not IP addresses. So this is what we mean with service-centric. We're moving away from like very networking specific terminology into a world where we care about services fundamentally and allowing them to connect together, and still allowing to bridge to the old world. And we'll get to that. So obviously you will not just run Kubernetes, you will also run legacy workloads or existing workloads. You still need to integrate them, but you want to move away from like a world that is based on just pure IPs and ports. Let's look a bit at the typical user journey that we're seeing, because I think this will be incredibly helpful to see where Cilium fits in. And many of you may be somewhere on this landscape. So let's start with like stage 1, stage 2, stage 3, and you will probably recognize yourself at some stage. So in the first stage, this is where customers or users start exploring cloud native, Kubernetes. They get initial clusters up and running. And what they mostly care about is basic pod connectivity, basic service connectivity, and some initial cluster hardening, which may involve container image scanning or things like configuration, security, making sure that the dashboard is not exposed publicly, and so on. That's stage 1. We then go into stage 2, and this is typically entered when you start running sensitive workloads in your Kubernetes clusters, or you start running multiple tenants. So for example, you have multiple application teams leveraging or using the same Kubernetes cluster. And all of a sudden you start caring about zero trust network security. You start caring about encryption. You might have PCI DSS or GDPR requirements that need you or require you to encrypt in transit. You want compliance monitoring. You need to prove that you're actually encrypting. You need to, for example, prove that you're using TLS, and so on. You definitely want app availability SLAs. You want to prove that you are responding or that your service is responding with successful HTTP codes. You want to see the latency of your HTTP enabled services and so on. And you may also care about efficient load balancing. You might run a lot of services at this point. And you most likely also want to integrate with external firewalls or some other appliances that still depend on IPs or still only understand IPs. So let's say you still have your existing firewall in there. It's pretty dumb and it can only understand IP addresses. And it's quite involved to change the rule set of that firewall. How does that cope with a container world where container IPs are constantly being reused? With static egress IPs, we can assign static IPs to workloads as they come and go, and they, let's say, in a certain namespace or parts with a certain label will always be represented with that same IP, so the firewall can actually understand this. That's what I meant with we can also integrate with existing environments if needed. And then as we see stage 3, customers or users, we're seeing like the full embrace of microservices, typically with a very active CI/CD pipeline. We see multi-cluster, we see demand for layer 7 observability, traffic steering. For example, I want to have A/B deployments. I want to steer 95% of my traffic to V1 of the service and 5% to V2 of the service. We see GitOps style policy guardrails. We see advanced security runtime, for example, advanced security with runtime and IDS. We see multi-cloud strategies and so on. So that's kind of typically the stages we 3 users go through. Cilium really focuses on stage 2 and stage 3. Obviously, Cilium can do basic pod and basic service connectivity as well, but where Cilium really excels is stage 2 and stage 3 with the power of eBPF. Let's look at the full feature set, and we actually covered part of this already. So Cilium is roughly cut into networking, security, and observability. In that initial networking bucket, we have obviously the CNI capability, which enables Cilium to be the network layer of Kubernetes. What's unique there is that we can be very versatile. So obviously we support IPv4 and IPv6, but then we can also implement a variety of different topologies. So you can run us in an overlay or tunneling setup. You can run us with BGP mode on on-prem settings. If you're running us in public cloud, we can natively use AWS ENI, Google Cloud ENI, or Azure ENI, so we can leverage the cloud provider SDN. Or we can run a hybrid model. We can connect clusters together, for example, a GKE cluster and EKS cluster. And for communication within the cloud provider, we use the local fabric, the local SDN. And as soon as you have communication across the cloud providers, we can tunnel and we can, for example, encrypt that. Then we have extensive identity and API-aware zero trust network policies, and we'll deep dive into that. So I will leave it at that for now. And then we have like the service mesh or the mesh functionality, which is the ability to connect multiple clusters together, but also to do service discovery across multiple clusters. So it's not just the connectivity, but it's also the service discovery angle. And as Cilium evolves further, we will add more and more of the traditional or typical service mesh layer 7 functionality. We already have a fair amount. The next release will feature full layer 7 load balancing control, as well as open telemetry support for tracing data. Then we have a load balancer. The load balancer can do both east-west, so between services in or across clusters, but also north-south. So like, for example, replacing a hardware firewall or a hardware load balancer that sits in front of your cluster. Here we're using like a maglev implementation, which has been invented or published by Google. Several of the other hyperscalers are using this as well today. So you can basically use the highly scalable, highly efficient load balancing technology that gives you high availability in your cluster, so you can feel like you're using the same load balancing technology as Google and Facebook in your own clusters. In-kernel transparent encryption, very important. We can do this FIPS compliant or FIPS compatible with the help of IPsec. So with the flip of a switch, you can encrypt all the traffic in and across your clusters. And then as we looked at previously, we can also integrate non-Kubernetes external workloads. So you can run Cilium on a virtual machine or on a metal machine outside of the cluster and then integrate that workload. Like, for example, let's say it's a metal machine with a database running on it. You can integrate that database into your Kubernetes cluster and treat that database as if it were running as a Kubernetes pod. This is one example, like why Cilium then uses eBPF to be better. It's called kubeproxy or Kubernetes services. The standard is to use an IP table-based implementation, which essentially resolves to a linear list of rules that have to be traversed for every new connection. With eBPF, we can use modern per CPU hash tables, which simply perform better, in particular at scale. So for those of you who have studied computer science, this will probably be very familiar. A hash table will simply have a much better worst case scenario and also a much better average scenario for search in particular. Let's dive a bit into the security side, because I think network security is not only segmentation. There is an element of visibility that is very, very crucial. We want to be able to not only enforce segmentation, which says A should be able to talk to B, but A should not be able to talk to C, or I want team A to be separate from team B, and so on. We also want visibility into this. And we will dive a bit deeper into this, but we want to have visibility on who is talking to who and what exact workload is doing this. We want to have a real-time compliance monitoring in this. For example, we want to be able to see and answer the question, how many of my connections leaving the cluster are not TLS encrypted or are not entering a TLS handshake. We want to see what are the TLS ciphers that are in use. For example, you want to know whether your applications are actually really FIPS compliant. Are they negotiating ciphers which are not FIPS compliant? You need to be able to answer these questions. All of this data should be going into your SIEM or SIEM platform. We support a variety of platforms here, Splunk, Elasticsearch, but with Fluentd that we support as well, you can pretty much feed this into any system you have. If you still want, this is kind of the flow view or the abstracted view, if you still want the more traditional packet mirror approach, where you actually mirror the real network traffic somewhere, we have a network tap functionality as well that supports PCAP, but also encapsulation, for example, injected IDS, such as Suricata, so you can filter and, for example, detect certain traffic patterns as well. So I wanted to deep dive on this one because I think this is very crucial. This is a very good example of why the existing way of network observability is very outdated. This is an example of AWS flow logs. And you may now say, okay, cloud is actually new. Like, why are you showing something that the cloud world has invented as outdated? This is a typical example why SDN as this second phase is actually incomplete for the container or the cloud native environment. AWS flow logs, just like any other network visibility product here from traditional providers, provide visibility based on IPs and ports and subverting. So we see this IP is talking to this IP on this port, and these are the number of bytes, and I am actually allowing this or I'm not allowing this. Containers reuse IPs constantly, so these logs are useless. Like you will not know what IP belonged to what container a couple of minutes later on. What you want is really something like this, and this is what Cilium gives you. You want to have a flow log that not only gives you the metadata, in this case, you see that there is like a namespace tenant jobs, and then there's a pod or a service crawler. You then also see the entire process ancestry tree. So you see that this is containerized. You see what container runtime has started this container, and you also see all the sub processes, all the processes inside of the container that has been spawned. And then you see the connections, these are the arrows, and the destinations. And in the destinations, you see a mix of DNS names. For example, when a connection went out to api.twitter.com, we actually see DNS name. But we also see internal names, such as the internal Elastic service. Even an example of layer 7 observability. So we see that this was an HTTP GET on /user/search on port 9200. Why is this important? Because what you're looking at here is actually like a compromised workload where an attacker has used or started a shell, started netcat. Netcat then reached outside to basically spawn a reverse shell. And then an attacker spawned bash and started running curl to actually perform a lateral movement attack and started looking around. If you looked at just the AWS flow log, just here, all of these connections would come from the same IP address, and they would be going to IP addresses that this service usually reaches out to. So you had no way of knowing that something got compromised here. When we understand like the actual workload entity better and understand processes and so on, we can detect and mitigate such attacks as well. So that's really the power of eBPF allowing us to do this. We're not just operating at the pure network level, because eBPF goes further and can, for example, also like hooking at the network, at the system call level, we can do this. I said I wanted to double click really quick on the network policy side. So I think what's very obvious is that you need to be able to do network policy on layer 3, layer 4. This means being able to segment services. Like, let's say I want my front end to talk to my back end, but maybe not to another service. And then you also want to limit it to port 80. So far, so good. That's what a standard firewall can do. Cilium can do more. Cilium can operate on layer 7 as well, similar to a VAF. So we can, for example, say, yes, you can talk on port 80 or port 443, but you should only be able to do an HTTP GET to /public. We can do this for other protocols, Cassandra, Kafka, gRPC, Memcached, and so on, like a variety of other protocols that we support here. Something very crucial and very handy as well is the DNS server policy. One struggle that lots of our users had was basically how to model something that reaches out of the cluster, for example, to mydomain.io, or another good example is AWS S3. So let's say a cloud provider database service, which is backed by hundreds or even thousands of IPs that are constantly changing. How are you modeling this in a network policy? Because there is not a single list of IPs which is static that is backing AWS S3. So how are you allowing this? So with DNS policies, you can basically model this as a DNS name-based policy, even with a wildcard. And what will happen here is that Cilium will basically hook into the DNS traffic and first of all only allow the names that are on the list. And if the workload is resolving any other name, even the DNS resolution will fail, but then only allow the IPs that are being returned by the DNS. So even if something like AWS S3 is potentially backed by hundreds of IPs, Cilium will only allow the 4 or 5 IPs that are being returned by the DNS server itself. So that leads to much better least privilege security. Last but not least, let's look into like the visibility aspect. So Cilium provides massive visibility thanks to the help of eBPF. We have service maps. That's what you see on the lower left. So this is kind of a graphical visualization of what services are talking to what other services. We can do this at cluster scale. We can do this across clusters. We can scope this down to a namespace. We can even run RBAC and, for example, say that certain teams can only see the service map of certain namespaces. Then we have extensive metrics from DNS, HTTP, network policy, network itself. Whatever Cilium can see, Cilium will expose as a metric. The favorite one is definitely like the dashboard that shows DNS resolution failures, because as we all know, it's always DNS. So that dashboard typically tells you immediately which pods are currently failing DNS resolution, or is DNS even a problem. And then on the right side, you can see the policy editor that's available under editor.cilium.io, where you can visually like show and edit and create network policy. So instead of writing YAML, you can create and visualize them in a graphical user interface. One small deep dive here, which I think is also cool. We see more and more users that want to have the application teams create part of the network policies, for example, the fine-grained policies, but then the security teams are not always willing to give full control over the entire network policy to the application teams. So we have created something called guardrails, which allow the security teams to impose rules on what application teams can allow, and then embed that into the GitHub or GitLab pull request process. And if an application team, for example, allows or wants to add a policy that allows to outside of the cluster, then the guardrails will come back and say, hey, this is not allowed. You need a security team member to actually approve your PR, otherwise you cannot merge it. But still allows application teams to, for example, define policies inside of the namespace. This is a deep dive on the Hubble observability that we showed earlier, showing what is talking to what. We can see here it's not only service to service, but we can go as deep as actually understanding the individual HTTP calls or Kafka topics and so on. This is great to even understand what is talking to what. In this case, we're seeing all in-cluster communication. This will also work for communication outside of the cluster or from outside into the cluster as well. And here, last but not least, the scale aspect. So Cilium has been designed from scratch for the container world. Unlike many of the other solutions that are out there, which have been created during the OpenStack days or very, very early Docker times, Cilium was kind of born with Kubernetes and has been created for the scale requirements of Kubernetes. So I think this is even slightly outdated. The biggest cluster we have at this point is about 250,000 pods across 20,000 nodes. So scale is never a problem for us, which is also the reason why more and more cloud providers, by now it's Google, AWS, Alibaba, that have picked Cilium as the default networking for their managed Kubernetes offerings because of the scale and because of the multi-cloud aspects. If you want to learn more about Cilium and performance, we're publishing blog posts on these topics relatively frequently. Just ping me and I can point you to them. This is the list of Cilium adoption, growing and growing, and that's it. So that was a brief intro into Cilium, Isovalent, eBPF. If you want to learn more about the company, obviously isovalent.com. If you want to learn about Cilium, the open source project, cilium.io, and eBPF.io is the community page we maintain on behalf of the eBPF Foundation. And with that, I think we have some time for questions, but I'm giving it back to Steve.
Thank you very much, Thomas. Highly appreciated your presentation. Let me see in the chat with Raphael if we have any questions so far, or in the audience between the speakers. If Adrian or Philipp have any questions regarding Cilium. In the chat, I don't see any pictures so far. We have a 30 seconds delay, but I don't see any so far. So
yeah, in case late questions pop up, feel free to join the Cilium Slack with thousands of users. There's many people there that can answer whatever questions you might have. So in case questions pop up later on.
Brilliant. Thank you so much, Stefan. So I just want to up. Here we go. So thank you very much, and Thomas. And now we will give the stage to Adrian to talk about the new project, Project Scene, managing Kubernetes with Cattle. So Adrian, the floor is yours.
Thanks a lot, Thierry, and merci beaucoup pour l'invitation. Alors, bonjour, bonsoir la Romandie. Thanks a lot for inviting us tonight. So I'm just going to share what I wanted to show you. There we go. So this is this screen. Very good. Good. So everybody should be seeing the proper window. So that's good. Perfect. Well, in that case, let's get started. So again, thanks a lot for having me tonight to talk about Project Scene. My name is Adrian Kosmaczenski. I'm developer relations at Vision. And I'm talking to you from the rather rainy, beautiful city of Zurich. It's been raining for the whole week, but it's okay. It's usually, it can be better the weather than today. So what is Vision? That's the big question, of course, and it's a little bit of an introduction. First of all, how do you pronounce the name? Because lots of people are asking VSHN. No, just Vision. This is why there's an I in the logo, okay? And we call ourselves the DevOps company. We've been in Zurich since 2014. We're 46 people working in Zurich, and the number 46 is important for the presentation, so remember that for a bit later. We've been providing since then DevOps, Docker, and Kubernetes help to many companies that require support 24/7 and with various certifications, because fintech and insurance are big industries here in Switzerland. So of course this helps a lot, and we have the privilege of having been the first company certified with by Google to be a Kubernetes certified provider. We offer our own platform as a service called Apuyo, where people can run OpenShift or Rancher. And tonight we're going to talk about Project Sin, which is one of our products. Another one is Kdup, which is a backup operator for Kubernetes, but this is not the subject of tonight. And of course, the usual list of very fruitful partnerships we have in the industry. You might recognize some of the names. By the way, we are remote friendly. Alors, si vous travaillez en Romandie, c'est pas un problème tant que vous êtes en Suisse. Si vous cherchez, c'est un peu un plug, mais voilà, on le fait quand même. Donc, mettez-vous en contact avec nous parce que franchement, c'est super cool de travailler chez Vision. Et je vous laisse l'adresse du handbook. I go back to English. So, if you would like to join Vision, we are remote friendly. No worries about that. Go to handbook.vision.ch. Learn more about us. We have a very special culture, so please join us if you want. Now, after this commercial break, the true story of tonight is about a little bit of history. I want to make you laugh. I want to give you some pointers. If you are a younger part of the audience, you might shake your heads in dismay. And if you are like me, you've been in the industry for a couple of years, you are going to shake your head in dismay as well and basically be very happy that we're in 2021. Then that will explain why we introduced Project Sin, and I'm going to show you and explain to you what it does and why we build it. And we're going to have a light demo. So I would like to show it to you in action. So I'm actually going to run and you're going to see live how it works, okay? And then of course, if you have any questions or answers, I will be very happy to answer them at the end. Very good. So let's do a very quick trip back in time, because it's the future. We are beyond the times of Back to the Future 2, right? That was in 2013, I think. Now we are in 2021. Let's go to 1996. And in 1996, we used to call, cloud native apps. There was no such thing as cloud native apps. There were web applications. So you were a web developer. Basically, there was no front end or back end extension. You were doing the whole thing. And most probably back end would be done in Perl, maybe Java, which was a hot new thing back then. VBScript, if you weren't lucky. Anyway, Objective-C, if you were a the web objects developer and your company could afford the insane license price of that product. JavaScript, if you were using Netscape application server, or even Lisp, if you were Paul Graham. In those times, we gave names to our servers. I don't know if you remember that time. There was a time where servers had names. So the least imaginative companies would call Web 1, Web 2, DB1, DB2. Maybe some startup would basically have Star Wars fans. So you would have Alderaan, Hoth, or other planets and other characters in the Star Wars universe. Or if you're a Lord of the Rings fan, you get the idea. We gave names to our servers. And we talked to those servers. We uploaded files using this thing called FTP, right? And not all of us were using source control. Some teams I know were using CVS, not the pharmacy company, for those who've been in America, the concurrent version system, right? So you would check out, and it was a bit cumbersome and not very reliable, but kind of worked. But it was much, much better than the competition, which was Visual Source Safe, which I wouldn't recommend to my worst enemy. So we didn't have clusters. Actually, most companies were very happy running with one Apache server, one or IIS, if you were in the Microsoft universe, maybe an Oracle or SQL Server database, and you would wire everything together. That's basically what we got. Hopefully you didn't have what I'm showing here on the screen, but you get the idea. Those were the times. 1996 was the time of the hardware server. And you would deploy a new version of your app once every few months. Let's move on 10 years in the future, right? We've got Subversions now. Subversion is great. You can migrate directly from CVS. So you import everything. It's a bit more reliable. It's concurrent commits. It's actually much, much better. We've got AWS all of a sudden because in August 2006, it went in beta. So you could start creating EC2 instances at that time. And in those instances, you had to install the full runtime and all of the libraries and everything required to run most probably Rails or Django apps, right? Those were the hottest frameworks of the time. From the Rails world came one of the first ideas of infrastructure as code, very early. For those who remember Capistrano, and Capistrano was great. You could cap production deploy, cap production rollback. But still, you would give names to your servers. That's basically what happened. And then, of course, Nginx came out. So people started using it for load balancing. So all of a sudden, you started having more servers with more instances of your app, maybe talking to the same database, maybe not, maybe load balancer for the database as well, who knows. More or less at the same time, and also written in Ruby, which was decidedly a very popular language, and it's still a very popular language, but back then it was exploding, we had Puppet. So Puppet was another milestone in the configuration as code idea. So basically, you would define everything that is needed to create this infrastructure. So clearly, most of what we creating as infrastructure was virtual machines. That was a big thing. It was starting the virtualization, with Xen and the VMware and everything. So everybody was starting to actually find ways like Puppet to spin up all of those virtual machines and to have some kind of infrastructure as code and a bit more agility. So you can say that 2006 was the age of the virtual machine, and you would deploy your app once every few weeks, which is already quite a thing. So let's move forward 2016, 10 years further into the future. So in Annus Mirabilis 2008, all of these things happened in the same year. Go language, Google App Engine, Stack Overflow, Azure, GitHub. And it didn't stop there. Apparently, the economic crisis of 2008 had a tremendous effect on the software industry, clearly. In 2011, we had OpenShift and Docker, and in 2014, GitLab, Kubernetes, and Terraform. So the world as we know it took shape. And in the meantime, Git took the world by storm. So Git has the possibility of importing Subversion repositories. So I'm pretty sure you've done that by now. And we started rewriting our apps, the 12-factor application principles, and we put them inside of containers. And everybody was talking about how the cloud had become this pyramid where you have infrastructure as a service, platform as a service, software as a service, or service as a service, a kind of a meta thing. But this is how everything was building up. And all of a sudden, people talking about DevOps and all of those things. And when we realized inside of our cluster, we didn't care about the names of our servers. We didn't have servers. You have like nodes and pods. Maybe your nodes still have names, but they are probably provided automatically by your infrastructure as a code tool. And right now, we don't treat our servers as pets anymore. They are just cattle. We bring them in, we bring them out, we kill them as we need. It's unfortunate, but that's basically what happens on these clusters. And this is basically the age of containers. So now we're deploying every few days. Now, let's see what's going on right now and why we think we need to go and to move one notch above. Right now, we have GitHub Actions and GitLab CI/CD. We build our clusters and our containers. We deploy all of our applications. Everything is automatized. We don't use Docker anymore. We use Podman. You don't use Docker Hub anymore. You use Quay or another container. We're very we are very dynamic. We can move from one provider to the other because thanks to Kubernetes, we got Kubernetes all over the place. You've got Kubernetes from AWS to Hetzner, CloudScale, Exascale, you name it. And even in your laptop, you can have Minikube, K3s, or Kind, or whatever. And then basically you're running your application locally on Kubernetes as well. And Kubernetes is big, big, big business. I mean, let us remember that IBM bought Red Hat for $34 billion. So it's big, big money. So basically, we are moving to the point, we think at Vision, that we are moving to the point where we don't treat our clusters as pets anymore. I'm not talking about servers, I'm talking about the clusters, because this is the age of the clusters, and we're deploying our application every few hours. Everything is accelerated tremendously in the past few years. And we believe that Kubernetes has won. The container orchestration wars, if there ever was one, Kubernetes took it over, and it's basically the platform that most applications are being run off these days or migrated to these days. And that is why Project Syn comes into play, and that is why we created Project Syn. Because the diagram that I showed before with those little boxes, actually those little boxes for us are clusters. We are managing hundreds of clusters for our customers. So we cannot afford anymore to just simply use infrastructure as code tools or even Terraform. We need something that goes beyond, in the sense that allows us to synchronize the settings, the applications, the deployment, the procedures, the policies over all of those clusters for our customers, so that we can manage them properly and keep a sense of sanity. Because as I said at the beginning, in Vision we are 46 Visioneers, and basically only 30 of them are actual engineers doing the job. So these 30 people are actually managing hundreds of thousands of services, instances of GitLab, instances of Kafka, instances of pretty much any application you can imagine we are running for our customers, and it goes into the hundreds of thousands of units. So we need better, and that is why we created Project Sin. So Project Sin is a set of tools that allows us to manage Kubernetes as cattle. So basically, we can have lots of clusters. We can bring them up, bring them down as needed with the same configuration, with reliability, with security profiles set into place, and everything clearly set up. And it offers many, many features. So for example, it offers the possibility of grouping your clusters on groups and tenants. So a tenant could be one of your departments, or one of your teams could be a tenant with many clusters. And all of those clusters will share the same the same functionality, the same features, the same policies. Everything will be coordinated among all of those clusters, and is full GitOps operations. Everything is based on Git projects. So you just push your changes, commit, push, and automatically the changes are picked up by all of the clusters of your tenant as required, thanks to Argo CD. There's a lot of tooling bootstrapping, so us as management teams for those clusters, we actually can install everything that we need, like Prometheus and whatnot, to get all of the information that we need on those clusters. We manage all of the configuration on a centralized environment. And we have reusable components. So Project Sin includes the possibility of being extended with a very simple procedure to create your own cluster. So literally your components. So literally anything that can be described in YAML for your kubectl to use can be put inside of a Project Sin component and deployed across all of the clusters of your tenant. We use a default toolset based on open source tools, and thanks to Renovate, we have automatically maintenance of all of these components. For secret management, we don't reinvent the wheel. We use Vault from HashiCorp, of course, and all of the service provisioning as well is automatically made available to all of the clusters. So in this demo that I'm going to show today, I'm basically going to install a little application over 3 clusters that I'm managing with Project Sin. There are 4 main components for all of this magic, and each one of them is a separate project on our GitHub page. First of all, we have the lieutenant operator that manages the CRDs, the cluster, the tenant, the Git repo. All of those objects are defined in Project Sin and are available as native objects for Kubernetes. Then we have the lieutenant API, which is basically the interface that it is used to talk from a managed cluster to the central cluster where all the management takes place. Okay. Then we have Steward, which is the agent that basically runs into each one of the managed clusters of your tenant, which in turn runs Argo CD. And Argo CD, you might have heard about it. It's a CI/CD tool for cloud-native environments. It's very cool. It works really well. And it basically is the thing watching the Git repos that belong to each one of your clusters in such a way that you are able to manage them. And then we have Commodore, and Commodore is a configuration generator that basically manages a hierarchical model, and it uses Capitan, and Capitan with K. Capitan with K, it's a template tool for Kubernetes. It allows you to template different YAML files, and basically you can generate YAML files based on different parameters. Each one of these projects is available on GitHub, and this is how it all ties together. On the right side of the screen, the blue box represents the management cluster. So this cluster is running, it's a Kubernetes cluster running Lieutenant. Lieutenant only runs on that cluster, and is the one who keeps the inventory of everything that's going on all of the managed clusters. One of them appears in green on the left side of the screen, and that one is running Steward, okay? So Steward basically connects to the Lieutenant API to say, here I am, it is me, please manage me, tell me what I should do. So lieutenant goes, checks into the inventory, matches the state of the current cluster and the desired state as well, and will basically give the order for Argo CD to synchronize and do everything that is required. So this is really basically how it goes. The pieces are colored as well in terms of the origin of those pieces, and the blue boxes belong to stuff that we've done in Vision. One of the things we can deploy basically is KDAP, which is our backup operator. It's just shown as an example on the left side. The orange ones are the ones from the Cloud Native Community Foundation. So we are leveraging a lot of tools that are actually publicly available and have become a standard for the Cloud Native space. Good. I mentioned that there's an extension points, which we call the Commodore components. So they allow you to customize and extend the number and variety of tasks that you can perform with Project Syn. You can customize and apply changes to all of the clusters using these components to ensure conformity, coherence, alignment, and reducing the workload for DevOps engineers, basically. There's a lot of Commodore components already ready to use on GitHub. Last time I counted, there were more than 60. We have a Commodore component hub as well. I'm going to show the URL at the end of the project. At the end of the presentation, you're going to see how many projects we have. A component is written in JSONnet. JSONnet, it's a small language that basically can be described as JSON with variables. It's a very simple way. I'm going to show you an example. JSONnet can export into YAML, which, as you can imagine, is exactly what we do. We need to export that so that we can talk to the Kubernetes API and perform the required operations. There's a lot of them already published in GitHub, and this is the URL for the Commodore Components Hub, is hub.syn.tools. You have there the documentation for all of the components, and we are publishing new ones every so often, and there's third-party ones because some partners are already using Project Syn in production, then they are using their own components, and they are sharing them in open source, which is great. In terms of competition, what we have, basically the two big ones that we've found that actually do something similar is Rancher Fleet from SUSE now, and Chaos Orbos, and it's another project that basically allows you to do GitOps management of several clusters as cattle as you need them. Very good. So let's go for the demo time. The demo is a very simple one. I'm running on my laptop right here a Minikube instance, a K3S instance launched via K3D, and a kind cluster. Okay, so I have 3 clusters, very small ones, running on my machine, and I use K9S. I don't know if you know K9S. You should totally use it. It's absolutely fantastic. So K9S, it's a command line management tool for Kubernetes that allows you to see in real time the state of your clusters. So that's why I use it. And what I'm going to do with all of that is to deploy an application that is contained on the Quay container repository. You can go and check it out. It's public. It's quay.io, and it's called Fortune Cookie Service. It's a Fortune cookie. So what I'm going to do is to run a Fortune cookie application, and I'm going to give you your future. I'm going to show you a lucky number that you can play in the Euro Millions at the end of the week if you want. So very good. I'm going to go back to my slides. Very good. And I'm going to basically, just for the sake of perfect, there we go, refresh my terminal. So this is K9S. K9S is a great tool. I love it. It works on the command line. So here in my terminal, I have 3 K9S, each one connected to different instances. So the one on top is connected to Minikube. And the Minikube, as I said before, is the one that I use to keep all of the catalog of everything in my cluster. And for that, I need Lieutenant. So I have the namespace Lieutenant. I'm showing the namespaces here, right? So this, you can see what I'm showing right now for those of you who don't know K9S. On the bottom, on the left side, I have K3S. This is a K3S cluster launched with K3D, so running on Docker. And of course, this one is managed. So it's not running Lieutenant, it's just running the Syn tools. And this one is a kind, cluster running on my laptop as well. So there we go, very similar in that sense. If I hit the enter key, I can see the contents of what I have running right now on my namespace Syn. And as you can see, there's steward, and Argo CD, because Stuart is driving basically the operation of Argo CD that is running on the cluster. And on the side of my Minikube, if I hit enter, I can see the pods running in the lieutenant namespace, and that's the lieutenant API and the lieutenant operator. So you can see all of the tools that are running. The Commodore tool, it's a Commodore, the Commodore tool, which is the fourth one or component of Project Sin, is actually run on the command line. So I'm going to use that right now. So the Commodore tool is available as a Docker container. So basically, I have written an alias because it's actually quite a bit of thing to type every time. So first of all, I get the lieutenant URL. So the lieutenant API is running on Minikube in my machine, and it's exported to the outer world using ngrok. So I'm asking ngrok, which has an API, very convenient, for the lieutenant URL. And I need a token. So basically, every time that I talk to the Lieutenant API, I need to pass a token, and this token is stored as a secret inside of my cluster. So basically, that's everything I need to get that very, very long password. And then I use that to do a Docker run. And I run what? I run the container called projectsin/Commodore. And I'm using a particular Commodore version. I'm not using the latest, I'm using a previous one, because this project is a work in progress. So there's something, a little bit of friction, but to make sure I'm using version 0.8 of the Commodore. So this is the version that I'm using right now. Another thing that I've done to make my life a bit simpler is a command called Commodore push all. So this Commodore push all command, what it does is basically to retrieve the list of all of the clusters that I have in my Minikube, in my management cluster. And for each one of them, I compile the catalog of all the things that I defined through Commodore that should be installed in all of the clusters, and then I push. When I push, that means that that goes directly into your Git repository. If you don't push, it basically just compiles and eventually will tell you of errors during compilation, right? Of course, the pushing is stopped in case of an error during the compilation. So what does all of this look like? So let's first of all look a little bit at the structure. And here you see that there's a folder which start with T called T Wispy Wood. What is T Wispy Wood? Well, I'm going to go here to my cluster, my Minikube cluster, and I'm going to see all the tenants that I have defined. And I have a tutorial tenant called T Wispy Wood. And this tenant has 3 clusters that are assigned to it. HSun, which is a K3s cluster, which is the one right here on the lower left. Then I have the Minikube cluster called Lively Smoke, which is the one on top on black, and Spring Frost, which is the kind one at right there. So I will go back to the display of my namespaces. Very good. So as you can see, K9S is a really nice tool for this. And if I go here, I will have a YAML file for each one of my clusters. And I have a very convenient one called common.yaml. Common.yaml, as I can imagine, it's specifically for all of the clusters in that tenant at the same time. So you can specify common things there. So I'm going to edit it. And of course, I'm cheating here. It is pretty much ready to show. I'm just going to uncomment this line, write it. And before I close, I'm going to show you here I have this component. I wrote a component for Project Sin, which is called Component Fortune. And this is the component itself. It is written in YAML. So if I go to this is an open project. It's completely public. You can go and check it out. And if I go to the component folder, there's a main file, which, as you can imagine, is the most important one. And basically here I'm defining YAML objects that will be translated into YAML. So literally I'm defining a namespace whose name is, and here it is, Sin Fortune. This is very important. This is the thing you should remember right now. I'm defining as well a service, and I'm defining a deployment. And the deployment, these 3 objects are very classic Kubernetes objects. And the image that I'm using, it's stored in this variable called container name. And it's the one that I just showed you, the Fortune cookie service, which is right there on Quai right now as we speak. So very good. That means that if I apply the Fortune application, I exit, I can then git commit added application and git push. So this is stored on a Git repo. Let me show you the Git repos. I have in my GitLab, in my private GitLab, of course, I have one GitLab project for each one of the components in my project's installation, each one of the clusters and my tenant as well. Okay, and basically now I can go back to where I was, and I can Commodore push all. So now I'm going to compile and push the catalog of all the things that need to be installed for each one of our clusters. And of course, this can take a little bit of time. I pray for the demo gods to be good to me in this moment. It's a little bit faster. I suppose that with all the networking that's going on in my machine or something, maybe it's a bit slower. Hopefully it will accelerate at some point. So it fetches all the components. Let's see how it goes. This is the moment where one would like to have a little boost on their machine. Oh, okay, well, it's going. Some things are happening. It's usually a bit faster. Let's try again. Well, it's going to take a while. So I will leave this running and I go back to the slides because my time will almost be over. And basically, I don't have much more to show, but the finished product. So we'll go back to the terminal when I finish with the slides. First of all, a call to actions. If you want to know more about Project Syn and what it does, go to syn.tools. That's the main website of Project Syn. And basically, we have as well our GitHub organization with all of the projects there. We have our Commodore Components Hub with plenty of things ready to use, ready to install, you name it, Prometheus, networking. There's plenty of different components for you to use. We've got a chat on community.apuyo.ch. Please join and ask your questions. If you do so, please abide by the code of conduct. And another interesting thing of Project Syn is that it's been designed in the open. So basically, every decision that has gone into the creation of Project Syn has been shaped through a design document, and all of them are available as well. There's a getting started tutorial to basically get the setup that I have right now on my machine. And of course, there's a Commodore Components tutorial that gives you a little bit of an idea of how to create a new Commodore component if you want. The current versions, as we speak, only Lieutenant is 1 point something. So basically, it's very stable now. The other tools are still a work in progress, but as you can see, we are advancing and publishing new versions very, very often. So basically, this is what I wanted to show. Okay, of course, what I wanted to show is this worked. Look, good news. This green thing that happened right here, it's basically that Project Syn has detected new stuffs, and we have a manifest for an application called Fortune with a deployment, a namespace, and a service. And that means that if I go to my K9S management console, my first cluster, right, because it goes in the order of the clusters definition. The first one is the K3S, and lo and behold, in my K3S cluster, I have my application running, and this is really cool. So what I'm gonna do is basically something very simple. I'm going to go to the services. I'm going to make a quick port forward. This is something as well that is really cool with localhost 9090. Let's see if this is running. Should be, hopefully. Forward, we have a port forward, yes. Wrong port, exactly. That's why. Go back to the services. So this one is listing the port 3000. That is why it's not working. So the local port is 3000. And let's try again. And bad luck. But I have seen Fortune running right here on my Minikube. That's a bit easier because in Minikube, my services are automatically exported through the Minikube service list, which I'm watching. So here, basically, when I click on here, I can see Cloud Native, Romandie, Meetup, Fortune Cookie of the Day. Surprise your boss, get to work in time. That's basically my message for you today. So thank you so much. My name is Adrian Kosmaczenski. My email is adrian@vision.ch. If you would like to use Project Sin for your own work and your own company, don't hesitate. Send me an email. I will be very glad to help you. And having said that, I stop sharing and I go back to Thierry.
Thank you so much, Adrian. I really like the tip of the day for my boss. I will try to see if my boss is watching and if I surprise him tomorrow by coming on time or earlier. Thank you so much again. I was wondering if there are any question in the audience. I'm looking at the chat. I don't believe that we do have any questions so far. So anyways, we'll have still 10 minutes at the very end after the third presentation, and like this we'll see if we have any other questions. So far, thank you very much, Adrian. And I wanted to just ask you one more questions, people. Just we'll have a 5-minute break, and you can scan the Slido and put the code 31543. So which cloud native topic would you see in the future meetups? What would you be interested in? Or if you want to share about your topic or share about your company or some ideas, please, by all means, we are all here. Sharing is caring. So now for this, we'll have a 5-minute break to take a coffee or have a drink of water, and that we'll see you just after the break with Kubestack. At the very end, I will present the topics that people are interested in. Thank you very much for joining back after this 5-minute break. So I will just see a couple of answers. What do we have from what people are actually thinking of up in the type of topics for the next future meetups? By all means, please continue to add all of your questions on the chat or the topic that you want to see sharing in the future. So we have Thanos, traffic, Arbor telepresence, and Docker Hub alternatives. So five ideas. So please, by all means, during Philipp Strube topic about Kubestack, please don't hesitate to add a topic or to add it later on. And now I will give the floor to Philipp up. If the floor is yours to talk about the framework for teams building Kubernetes platform using Terraform with the developer experience focus.
Yes, thank you. Thank you for having me. So I should be sharing my screen now.
Yes, you are.
Perfect. So I think I don't think this was planned, or maybe Thierry planned this, but it was very nice for me to be speaking after Adrian here, because Adrian gave such a great summary of how we ended up in this place, in the cloud native world, and it's very much my own history as well. So I dropped out of law school in 2009 to start a PaaS company called Cloud Control. And while Cloud Control, like most public PaaS companies of the time, didn't quite make it. So if you go to cloudcontrol.com today, you'll end up on a Swiss company, a very nice Swiss company that you may know called Exoscale, which acqui-hired us back in the day. I basically have a history of running containers in production for a very long time, right? And I dropped out of law school to go into the platform game. And while the PaaS company didn't make it, as I said, a lot of companies insist on building their own internal platforms. And that's something I have a lot of experience with and that I'm basically enjoying doing right now. After doing this plenty of times from scratch, like almost everybody else, I thought, well, there must be a better way because this is getting really boring. And so if you take a look at the application development ecosystems, you are probably very familiar with a concept called frameworks. Right? The idea is that if you need to write a cloud native app in Java, you're probably not gonna, I mean, there's always the odd one out, but you're probably not gonna start writing everything in vanilla Java from scratch, HTTP routing and so on. You're probably gonna use a framework. Spring Boot seems extremely popular, right? But there's like plenty of examples for frameworks that are case specific in all of the languages, Ruby on Rails, Python, I don't know, Flask. It's an unlimited supply of frameworks on the application development side. And most of them, if you have the same use case that they are built for, you probably get a lot of benefits from starting with such a framework. The infrastructure as code world, however, is slightly less mature or significantly less mature. Right here, everybody seems to be building Terraform from scratch every single time. And I'm basically out here trying to change this. So when I say Kubestack is a Terraform framework, I mean that in the exact same way as if I were to say Spring Boot is a Java framework. Right? And another thing that was nice, because Adrian was talking right in front of me, is Kubestack has a very specific use case, which is you can use it to define clusters and cluster services. I'll explain in more detail when I'll show you everything. That's why you see my Visual Studio Code there. We're going to look at a lot of code now. But basically, that's what Kubestack does. It allows you to define your custom Kubernetes platform based on clusters. Multi-cloud, I support all the 3 major cloud providers, AKS, EKS, and GKE managed Kubernetes offerings. And what I call cluster services, Ingress, Istio, certificate manager, right? All the kind of stuff you need on your clusters before you can deploy application workloads. And that would be a good fit here, in my opinion, right? You could use Kubestack to put up a bunch of clusters and install Syn on top of it using Terraform, and then Syn can take over and do the application deployments. Of course, it's a very crowded field for the application deployment side, right? There's Flux, there's Argo, countless others. Yeah. All right, so I'm asked to be zooming my visual code here. How's that? Is that better? Oh yeah, you can probably tell me in 30 seconds. All right, so as I said, what we're aiming for here, or what I'm aiming for with Kubestack, is basically the kind of developer experience you're used to from application development frameworks. And so I'm in this demo folder here. And so very similar to how you would usually have some sort of CLI for your favorite framework to scaffold a new repository for you, Kubestack can do that too. So you can do Kubestack repo init. And then here you get to pick the cloud provider that you want, like for example, AKS, and you press enter. And then if I press the refresh button here, because this is remote, you'll see it created a new directory here with a Git repository in it and a scaffolded Terraform setup for an AKS cluster. Gonna have a quick look over at what the files here are. Right, so you have a bunch of Terraform files. They're all prefixed with a cluster name, because of course you can do multi-cluster, multi-region, multi-cloud. So to know which one is which, I prefix them like this. It's a convention, of course, you can name your Terraform files any way you like. So AKS0 cluster has the cluster module in it, and we're going to talk about the configuration here in a bit. And then there's an example for a cluster service that's always included, is this default ingress setup with Nginx ingress. And so there's a Terraform module that puts Nginx ingress on top of that cluster and configures it. And there's the providers file here, where you configure the providers specifically for that setup, right? If you go multi-cloud, you'll have a bunch of these different providers that you need. There's versions TF, it's Terraform convention requirement, where you define non-HashiCorp providers mostly, right? In my case, this is the customization provider that I maintain as part of Kubestack. And there's 2 Docker files, and there's a manifest folder where you can put your Kubernetes YAML. So that's the quick overview. I've prepared a second one here, which in this case is GKE. And in this one, I want to show you a little bit more about the configuration. So if I open this cluster file here now, the GKE cluster file, what you see is there is a hash map called configuration. And the hash map has multiple keys, apps here, ops down here, and then lock down here. So Kubestack uses Terraform workspaces for different environments, right? And so that means you have one Terraform code base. And when you move your changes through your infrastructure environments, you would do so by selecting a new workspace. I'm going to show this in a little while, right? But basically, the keys of the hash map here match the Terraform workspace name. So if in the console down here, I do I'm not in the, I'll show you that later. The second thing to know is that basically inside each hash map, you have a variety of keys, and they're basically the keys how you define how you configure those cluster modules to bring up the cluster that you want. There's a couple of things that you have for every cluster module. So name prefix, base domain. I'm always asked for these 2, no matter if it's AKS, EKS, or GKE. So these are Kubestack specific. They're the same for all cluster modules I offer. But there are also some which are cloud provider specific, right? So project ID, for example, is something that Google needs to know. In AWS would be an organization, but you configure that on the provider level. So there's some differences, but I try to unify the experience across different cloud providers as much as possible. So you have a common base how your Terraform is structured when you use it, even in a multi-cloud setup. So name prefix and base domain, they're basically used as part of a module that all the cluster modules use, which creates unique names across inside the same cloud, inside the same region, also across regions and across cloud providers, by basically putting a prefix in front, and then you can read the comments here later, basically, or look it up in the documentation, where it assembles fully qualified domain names based out of a lot of different aspects, like the prefix, the environment the cluster is in, the region the cluster is in, the cloud provider the cluster is in, and the base domain, right? So in this example here, cluster name would be Kubestack Apps Europe West 3, and then cloud provider is GCP, and there's infraexample.com, and it will provision DNS zones for you in the respective cloud providers DNS offering, right? So Route 53 for Amazon, Google Cloud DNS, etc., etc. And then there's a couple of other settings you can set here. Like what version you want initially for the initial cluster. It's updated automatically, of course, for GKE. The machine types you want for your default node pool and how many nodes you want, and on what region and what node locations. So the second thing about the configuration here is that Kubestack's configuration is inheritance-based. This means you define all your settings in the Terraform workspace, which is the one that will be running your applications later. So this is the mission-critical one. By default, all other environments inherit all the settings from apps. The purpose of this is that it makes it explicit what changes there are, and since you move any change from the less critical environment validated there before you promote it to the critical environment that runs your application, having no differences in the configuration between those two environments means it reduces the risk of something that you just validated in one environment breaking when you promote it to the next environment. However, of course, you don't want exactly the same configuration for environments. Sometimes you have to have changes. And the way this is implemented here is you can overwrite values that you inherited. The benefit here is that you see in ops, there's actually 3 values I overwrote. And it makes it very explicit, right? What you changed from the apps environment. Of course, any change slightly increases the risk, right? So you need to, it's your judgment call to decide what can you safely overwrite and still have the pipeline successfully validate changes before they are promoted, or what you can, what you maybe should not overwrite. And so what I am overwriting here is basically, since the ops environment wouldn't run any workloads, all application environments by default would run on the apps environment. Of course, you could change that. It's up to you, right? It's a framework. You can modify it. You can also have multiple mission-critical environments, like a lot of bigger organizations. They prefer to have a split between non-prod and production workloads. So the way you would do this is, instead of just having apps here, you would also have another environment. Maybe let's call it apps prod, right? And then you would simply have 3 total environments in the cloud, and you would promote first to the non-critical app environment and then to the critical app environment. But getting back to here, since ops doesn't run any application workloads, you usually don't want it to use the same instance types as your production, right? As your production clusters that run application workloads, and you probably don't want it to autoscale between the same amount of nodes. So what this does is it overrides the instance type to have a smaller instance type here, E2 medium, which is one of those shared CPU core, so it's rather cheap. And the production one, the one that runs application workloads, in this example uses E2 standard 4. And then I also decrease the value for min node count and max node count here. And so in Google, in GKE, min node count and max node count are multiplied by the amount of locations. So you will have the apps cluster autoscale between 3, so 1 times 3 cluster node locations here, and 6 times 3, which is 18, if I'm not mistaken, right? So the production apps cluster scale between 3 and 18 nodes with this setting, autoscale. But the ops one would only autoscale between 3 and 6. You can probably make this smaller as well, right? You could put a 1 here, and then it would be autoscaling only between, it wouldn't be autoscaling, it would be 3 nodes, 3 of those small nodes all the time. If you wanted to go even further, you can, of course, also override cluster node locations like this, right? And you could say, well, the ops one I only put into 2 zones, and then I set this to 1, 1, and so you would have 2 nodes for the ops environment here, okay? So that's basically the idea here, what you can do. Let me look at my notes real quick. Yeah, so we just looked at how you can use this to have slightly different settings between ops and apps on the infrastructure level. And I said the other thing that Kubestack manages is cluster services. So the first example I have here is this Nginx Ingress module. And you'll see all modules, they have the same concept. They all have this configuration hash map, again, with the per environment keys. And inside here, any one of you who has used Customize before might recognize these keys, so patches and replicas here. inside the configuration for any of those cluster service modules, you can use any of the customization attributes that you could use in a customization YAML. Patches, namespace, prefix, all that kind of stuff. The benefit is, by defining the overlay, which is what Customize calls these, in Terraform, you can use values from Terraform, like here, for example, in this patch. This module will take the entire Nginx YAML from upstream as upstream releases that, and it's bundled in that Terraform module. And the version of of Nginx Ingress you would get with this module is 0.46.0. There's a newer version now, but I forgot to update my little demo here. I think they are at 1.0 now at this point in time. And so you control with the version of the Terraform module what version of Nginx you get. And what this patch does basically is the Nginx upstream will include a service type load balancer. And this patch here changes the load balancer IP that the Kubernetes service will use to the one that the cluster module registered as reserved with Google Cloud in this case, and that the cluster module already put into the DNS zone for you, right? And so this Terraform variable here, or this module output, gives you that IP address and patches it into the Kubernetes YAML. I think what's interesting about this is that you can consume upstream YAML entirely unchanged. It's very, with Customize, right? This is a benefit of Customize. It's very little risk of something requiring you to make a lot of changes to, for example, a Helm template. They can be, when upstream make changes, they can be quite a lot of effort to keep the template also updated with upstream changes. This is slightly better with Customize. And all I'm doing here with this customization provider that I maintain as part of the framework is basically I bring this into the Terraform world so that you can use values from Terraform to define those customized overlays that change the upstream YAML. And I go the little bit of an extra route to give you a Terraform registry that gives you Terraform modules for a selection of, it's currently a small number, but I'm trying to extend this, of popular upstream Kubernetes services like Nginx, Cert Manager, we will see in a while, and stuff like this. And the other thing is, you see I'm using this customized replicas here. This basically says for the apps environment, I want 3 pods, 3 replicas of Nginx Ingress controller, right? But again, we have the overwriting down here. So here I'm overwriting the replicas part. I'm not overwriting the patch because the module will always return the correct IP address for the environment anyway, right? Because the modules and the cluster services, cluster modules and cluster service modules, they all live inside the same Terraform workspace. So that IP address is correct by default. But here I want to manually say, well, on ops, I don't need Nginx to be 3 pods. It doesn't serve any traffic. I'm good with having just 1. Okay? And so that's an example of a cluster service module that you can use to put services on those clusters that you need before you can deploy application workloads. That comes from the catalog. So there's a pre-built module that has these Terraform capabilities, but bundles the upstream YAML. Of course, the catalog doesn't have all the, it has 6 or 9, or I don't know, some number like this, different services currently. So there may be other stuff that you might need too, or you may have bespoke Kubernetes YAML that you want to apply, but you want to do it in the same way. And for this, I have a second type of cluster service module, which is called the custom manifests module here. And what this basically does is it works exactly the same as those Ingress, Cert Manager, etc. modules from the catalog that bundle upstream YAML, but it doesn't bundle any upstream YAML. And you can provide your own. So what I'm basically doing here is I'm saying, okay, the module points to a customization that I already have on disk. And if I go into this manifest folder here, you'll find this MongoDB, right? And you'll find a bunch of standard Kubernetes YAML files with the customization here that groups them into a customization so you can point at it. And these YAML files I just got from the upstream release of the MongoDB community operator. And then by wrapping the module around it, I can basically have them included in my Terraform lifecycle in the exact same way as any other resource in Terraform. Okay, last example is another one from the catalog, which is a certificate manager. And if you've deployed certificate manager before, what this basically gives you is the certificate manager control plane. And if you want it to be able to return certificates for your Ingress then you have to configure an issuer, as it's called by Cert Manager, right? And this is the same way here. So this module does bundle everything that Cert Manager release upstream includes, all the upstream YAML. But additionally, you want to include your issuer, right? And so I can have this additional resources attribute here, where you can give it a list of additional YAML files that you want to also be included with your Cert Manager YAML. And I'm going to go, well, this one is not namespace, but if it would be in the same namespace. And then when you go to manifests again here, you'll find I have my little YAML file here with a cluster issuer in it. That's why I said it's not namespace, right? Because cluster issuers are cluster-wide. And then you just have the regular spec for how you define an issuer with Let's Encrypt. And the module will put both Let's Encrypt control plane and the issuer onto your cluster for you. All right, so what's we're going to talk about next? Yeah, so I said this all is included into the Terraform lifecycle. So what I'm going to do is I have this little make file here that jumps into a container image. That container image is provided by the framework as well. It bundles Terraform in a specific version and a bunch of the cloud provider CLIs, right? And it's available in different flavors. So if you are single cloud, it's slightly smaller, but if you are multi-cloud, there's a multi-cloud image that would include all of the cloud provider API CLIs, Terraform, I don't know, a bunch of other, like JQ and a bunch of other helpful tools. And the container image is used either during CI/CD, so that you always have an environment to run Terraform in that meets all the requirements, or you can use it for bootstrapping, like in when you follow the tutorial, or in emergency situations, right? If your pipeline doesn't work for any case, you can jump into that image and you have a working environment to be able to run manual Terraform commands if you, for whatever disaster recovery reason, may need to do that. And I'm not going to lie to you, many of you might have used Terraform before, right? There are certain situations in a Terraform lifecycle where you have to run manual commands. Like, I don't know, there's sometimes provider upgrades that require this, and a bunch of limitations that Terraform might have around for each, that you might hit this, etc., etc. So that's what the image is for. And so what I can do in here now is I can run Terraform commands, and I can run, for example, Terraform plan, and it should tell us that there's no changes because I deployed this cluster on GKE with all those Terraform resources beforehand. I'm going to make this slightly bigger here. What you see here is that you have these kind of resources, right? And what you have here is the GKE0 Cert Manager module. There's a customization resource. And that's, I think, something I like to highlight in comparison to integrating Helm or kubectl with Terraform. The customization provider will track every Kubernetes resource individually in the Terraform state, like this. And if I make a change to any one of those, like, for example, I go back into my ingress file here, and I go down here and say, well, on ops, I do actually want 3 now. I can save this file, and I run the Terraform plan at the bottom again now. Then you will see a Terraform plan that will tell me exactly what change it will do to which resource inside the Kubernetes cluster. And so what it will tell us is that the apps v1 deployment ingress nginx ingress controller will have one change, which is the replicas attribute will change from 1 to 3. Right? And so if you've used, for example, the Helm integration before, you would know that here, what you get in the Terraform plan isn't the change to the actual Terraform resource, it's the change to the Helm, to the values you input into the Helm template. You would only see that, right? So that's, I think, quite useful differences between this is implemented. And that's also the main reason why I maintain my own Terraform provider for this integration, right? It's that I can consume upstream YAML without changes, which makes it very easy for me to provide the catalog, because those customizations, they almost never break when upstream changes something. So I have a pipeline that basically rebuilds new version automatically. I look over it, I press the merge button, I have a release. It's kind of like this. I want to even automate it slightly more. But with the control of writing my own provider, I have the ability to define that customization in Terraform code, which means I can use Terraform variables, loops, module outputs, etc., to customize those Kubernetes resources. Okay, and so that's basically the setup. Now, one last thing, Kubestack will also, by default, suggest a GitOps workflow for your team to maintain this. And the way it does this is, I said already that you have one code base and you have different Terraform workspaces. So if I do Terraform workspace list here, you'll see there are the default I'm not using, but it's always there. You see ops and apps, and you will recognize these from our configuration hash map keys, right? So those are the two environments that are configured. You can have more, you could have less, you can call them differently, it's up to you, but this is the default. And the workflow, basically, if you follow the tutorial, it will give you a GitHub Actions pipeline file by default, but there's a repository on the Kubestack GitHub organization. There's a Jenkins example and GitLab example and Azure DevOps example, and I've done implementations for Circle CI for customers. I don't really care. Like CI/CD tools are all the same, if you ask me. And the workflow that Kubestack suggests, which is also documented on the documentation page, is basically to say any feature branch that anyone in the team creates will run the pipeline and give you a Terraform plan to show you what changes to the ops environment you can expect if you merge this into the main branch now. If you merge it into the main branch, the Terraform pipeline will run again, will select the ops environment, but instead of just running Terraform plan, like before in the feature branch example, it will run a Terraform apply and actually make those changes automatically against the ops environment. Now remember, the ops environment doesn't run any workloads. It doesn't run any workloads to be able to validate any change to the Terraform configuration, to enable any team member to merge at any point in time without being afraid of breaking anything, right? Because that's, I think, a big barrier that a lot of platform teams face, that anything they want to try has the risk of breaking somebody else's day, right? If you run the development application environment on the ops cluster, and whatever you're trying right now here in the Terraform configuration doesn't work out, you take the ops cluster down, you may be preventing, I don't know, 20 of your application development from working. High stress situation, I don't want to be in that situation. So ops environment would validate that configuration by applying it against real cloud infrastructure, even if the instances might be slightly smaller and slightly less of them. And if everything works in the ops environment, then you can promote to the apps environment, which you would do by setting a git tag. So you tag that exact same git commit that you just validated with a git tag, which triggers the pipeline again. But this time, the pipeline will run a Terraform workspace select apps first. Oh, sorry. I said the word select, but I didn't type it. So select, then you switch to the apps workspace. And now any Terraform apply, plan, whatever you run, would apply against the apps environment. And so if I do a Terraform plan now here as an example, you'll see that it wants to create a lot of resources because I haven't actually bootstrapped the apps environment first. Sorry. Yeah, this is one of those cases I wanted to show you perfectly. So if you are bootstrapping the Kubestack setup, you'll find that the tutorial tells you to first Terraform apply just the cluster module, because we're using for each, and the IP address for Nginx is unknown until you've applied it, right? You reserve one from the cloud provider, it will give it to you back to you after apply. And for each can't, in Terraform is a limitation that you can't use for each if the value you're depending on is in this known after apply state. And so that's why for Bootstrap, you have to first Terraform apply just the module. I'm not going to have you watch the entire apply here. Okay, so what's wrong here now? I have to type -target here. You'll see that I haven't created any of that. So the apps environment is entirely empty. It would now create all those 13 cluster resources. And then once you've applied with the target here, you would then apply without the target to bring up all of the stuff on top of the cluster. I'm pretty much out of time. There's just one last thing I wanted to show, which is a second example I have here, which is called Kubestack Starter Multicloud. And so this is an example of how it looks like if you were gonna define multi-cloud clusters with this, right? You have 3 files here that are prefixed with AKS, the cluster, ingress, right? And the cluster and an ingress for EKS, and a cluster and ingress for GKE. And so by doing this, in Terraform, you can bring up those different providers, managed Kubernetes clusters, and you can unify the application environments on top of them by specifying the ingress, etc., cert manager, anything else you want in Terraform. And yeah, so that's basically what Kubestack does.
Thank you very much, Philip. We have 3 questions. The first one is, can Kubestack work with a kind cluster?
Yes, so actually I haven't shown this, but if you go, let me go out here. The Kubestack command line client has a command called kubestack local apply. You can launch this in any Kubestack repository, and this will read the Terraform code and switch out the cloud provider modules with alternatives I maintain that use kind behind the scenes. So what happens is basically you have the GKE cluster module here, and has a source. What the command line client does is for every one of these modules that I maintain Google cluster, there's also Google cluster-local. And so when you run kubestack local apply, it switches out those module sources. It does this not in your live code, but inside a Docker container. And then it brings up representations of all the clusters you've defined in Terraform faked with kind. But then it will also put all of those cluster services on top of those clusters. This is the first thing you do when you start the tutorial. I think it's a nice way because this one will basically now watch your repository. And whenever it's currently applying all those Nginx English stuff, whenever you make a change to any of the Terraform files and you save it, it will automatically reapply this to your local environment. And so you get the kind of workflow that application developers have, right? With auto-reloading web apps that refresh the browser and you see your changes almost immediately. Of course, Terraform is slightly slower, right? But if it's a small change, like for example, if we go into this ingress file here and we change the amount of replicas here, and now when I save this file, you'll see that it automatically kicks off, sees the change at the bottom, and will now redeploy Nginx with just one pod on this local representation, right? So basically, I have this integration. I think it's very useful if you work on cluster services. However, of course, this has limitations, right? If you work on something like your VPC setup of your EKS cluster and the CIDRs attached to it, right, then it doesn't mirror this locally, right? That's where the limitation is. For changes like this, you still have to fall back to the Terraform plan kind of feedback cycle.
Thank you. So I hope that answers to AJ's question. And 2 questions from Sebastian. Can Kubestack support multiple node pools per cluster, or should we just need to add Terraform resources for that?
Yes, so Kubestack does support them. Currently, however, I have 2 types of modules I provide. So it's a little bit like the Git CLI, right? There's porcelain, and then there's the, what they call it, piping, I think, or something like this. Commands, right? You can use both of them, but the porcelain ones are the ones that are less likely to have breaking changes, and they're slightly nicer to use. I do the same thing. So if you look here, this Google cluster module has the configuration with the inheritance, etc. implemented. There's also a low-level module for node pools, which is used by this one to bring up the default pool. And you can use that to add additional node pools. What I don't have yet is a very nice Google node pool module. I'm currently working for a big automotive company, building a multi-cloud platform based on Kubestack with them. And currently they start on EKS and GKE next. So I'm currently building a very nice porcelain node pool module for EKS. You can see it already in the Kubestack repository is all open source, right? You can see it in there. It's a pull request. And then the Google one is going to come next. And then afterwards, I'm going to also have the AKS one. So short answer, you can do them. There is a module, but it isn't all the bells and whistle like the other high-level Kubestack modules. And if you want that, you can wait a little bit. But of course, nothing keeps you from, right? It's just Terraform. You can write your own modules, put them next to those. You can also put naked Terraform resources in the root module, right? And then have them add node pools to your cluster. So you have all the control you need. And I'm just trying to give a slightly better developer experience and also soon for node pools.
And do you support blue-green cluster upgrades? And how?
Yes, so you can do that.
Please.
Just like you can go and have multiple clusters from different providers here by just calling the module multiple times, right? I could also go here, instead of having GKE0 here, I will also have GKE1, call the module a second time, and then have two clusters. I apply that, second cluster comes up, and then I just go in and delete the 0 one after I moved all the workloads, right? This is how you can have a blue-green deployment. Temporarily, you define two clusters, and then you remove the one or the other, depending on which way you go, right? I don't usually recommend this because a lot of workloads will be persistent. The volumes, they don't move across clusters easily, right? So most of the managed Kubernetes offerings seem more tailored at in-place updates of those clusters. That's also what Kubestack does by default. And this is why I have this system of multiple environments where I validate all those changes against the cluster that doesn't run workloads before I promote them to make those in-place updates less risky. But of course, it depends on the application workloads that your team wants to put on those clusters, which strategies are best for you.
Super, thank you very much. So far, I think that's all the questions that we have in the chat. Maybe they can come up in the next couple of minutes. Thank you very much, Philipp. Highly appreciated. So now, do you have any last word or anything to close this session, or that was just answering this the
Yeah,
question?
so I think, right, it's an open source project. You can go to kubestack.com, follow the tutorial and give it a try. If you have any questions, there is a hashtag Kubestack channel on the Kubernetes Slack. You can find me and a couple of hundred other people there. I'm always happy to answer any questions that you may have. And then I'm always happy if people leave a GitHub star. It actually does help a lot. For some reason, people really like those.
I hear you. Thank you so much. Thank you very much, Philipp, for attending. So just to let you know, for the next meetups that we have planned, we have for Cloud Romandie, so Thursday, November 25th, and to end of the year, and the last but not least, and then to start the year happily for 2022. There is an error in my a mistake in my slides, so that will be February 3rd. As well, we like to share that we are part with Adrian from Vision, and with a third company, Puzzle, placed in Bern. We are part, the three of us are part of the Swiss Cloud Native Alliance. And so the next events from the Cloud Native Computing Switzerland meetup in Zurich that are organized by Adrian will be in a couple of weeks, October 21st.
Exactly, 2 weeks from now, on October 21st, at this time, pretty much at the same time in the evening, around 4 p.m. we are starting, so please join.
Awesome. Thank you, Adrian. And so to start the year as well, already has book your agenda for February 24th and May 19th. Are they in English or are they in German?
We do them always in English because there's a lot of people that come to Zurich to work and they don't necessarily work or even speak German. So the thing is that for February and May, we are aiming for an in-person series of events for 2022. So that will be as well a change. The October 21st is still online. So you can basically join on the Cloud Native page on Meetup, and you are going to see those events. But for next year, we would like to go personally and just meet the people, enjoy a beer, a slice of pizza and stuff like that. So we really aim for that.
We will make sure to come up then.
Absolutely, you are more than
Just for the
invited.
beer and
All
pizza.
of you
Maybe
watching
stay for
this,
the talks.
please join us. It's a great event. It's not so far from the Hauptbahnhof, the main train station in Zurich, so it's very easy to get by and to go back to wherever it is that you're living.
Thank you so much, Adrian. So last but not least, it's to know a little bit what are you interested in? What did you like the most about today's event. It's always great to know like this we can replicate or we can improve. So by all means, please share your thoughts on Slido, and like this we know where we can focus a little bit more. So this being said, so we can see a little bit of the polls, actual active polls, and but I leave it open until a few more minutes because it's past 7, and I think everybody wants to go eating and drinking and take it off the mic. Just we want to really thank you for Cilium and Vision and Kubestack for the presentations, and of course Camp to Camp for sponsoring the event and organizing it. If you have any type of questions, as all the speakers mentioned, and if you're interested in their slides, please let us know on the meetup, or let us know as well in the chat, or connecting with us, and like this we'll be able to share the slides after the show. Thank you so much, Adrian. Thank you, Philippe. Thank you, Thomas. And we never heard him, but thank you, Raphael, for being the editing in the editing room. Thank you, everybody. Have a great evening, and thank you for joining.
Thanks a lot, everyone. Have a nice evening. Bye bye.
Thank you. Bye bye.
Bye bye.